Welcome to Brain Vision.
In part A, we want to find the tension of the three ropes. By symmetry, I know the tension in the left rope is equal to the tension in the right rope, since the situation is entirely symmetric. And so really we only need to solve for two tensions here. Now I've drawn the left ball here in order to identify what the angle is. We know that this length here, which is the length of rope B, is 35 centimeters. The radius of this is 12.5, and so this entire length is 35 plus 12.5. And then this opposite length is just the radius, which is 12.5 again. This lets us say that the sine of phi, which is the angle from the vertical, is equal to the opposite, which is 12.5, over 12.5 plus 35. When you solve this for phi, you get a value of 15.26 degrees, and this will be helpful in the future. So now I'm going to draw some force diagrams. The first force diagram I'm going to draw is for the left ball. And so I have a normal force pushing to the left, which is from the right ball. I have a force of gravity, mg, pulling down. I have the tension in the rope, Tb, and then I have the vertical components of the tension in the rope and the horizontal components. So this would be Tb sine phi, because remember, this angle here is the angle phi. And that means the vertical component is Tb cosine times phi. So that's the force diagram there. We also are going to look at the union of strings or wires. We're going to draw the force diagram there. So if this is the union, we have tension A pulling up. We have tension B pulling there and tension B pulling there. Again, these are the same because the situation is symmetric. And this angle is again phi. So now we can start applying Newton's second law. The sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, which is equal to 0. I'm going to apply this to the left ball for that guy. And this implies that tension in B times cosine of phi, which is just this top force, is equal to mg. This means that tension of B is equal to mg over cosine phi. And then whenever you substitute values here, you get 152 newtons. And so that takes care of two of the wires, because both the wire going to the left ball and the wire going to the right ball will have a tension of 152 newtons. And so now we just need the tension of A here, this tension in this rope. To do that, I'm going to do the sum of the forces in the y is equal to mass times acceleration in the y, which is equal to 0, except I'm going to do this for the union now, not the left ball, for the union of the wires. This implies that 2 times tension of B times sine phi, because there's two of these wires and they give the same contribution, so I could just multiply one of them by 2. And that's equal to tension in A. If you're confused about where I got that, just go back to this picture. The one of them is going to give you Tb times sine phi, and then the other one's going to give you another copy of Tb sine phi. And then it's in the opposite direction of Ta, so it's equal to Ta. Now we found what tension in B was just a moment ago, and we know what phi is, so we can solve this for the tension in A. And when we do that, we get 294 newtons. And so that completes part A. Part B is asking for the force that the balls push on one another. And if you go back to our force diagram, that's just equivalent to this normal force here. And so I'm going to do Newton's second law in the x direction. Again, it's equal to 0 because these aren't accelerating. I'm going to do it for the ball. And this implies that the normal force minus the other x component, which is tension B times sine phi, is equal to 0. And we know what this stuff is, so we can just solve for n. And we get 40 newtons. And that's the final answer.